Let's look at theorem 1.15, unique linear combination, which states the set W1 through W sub k is a basis for W, which is the span of those vectors, in Rn if and only if 0 is a unique linear combination of W sub i's. That is, R1, so this linear combination equals 0 implies that R1 through Rk equals 0. So to start the proof, we're going to go, this means we're going the if-then statement. So if this is a basis, then 0 is a unique linear combination. So let's suppose first that W1 through W sub k forms a basis for W, a subset of Rn. So by the definition of basis, we're going to be using that a couple times. By the definition of basis, this linear combination is unique. So the R1 through, right, that's unique. So it's basically saying up here, W is a basis, means that every vector in W can be uniquely expressed as a linear combination of those vectors. So 0 is a vector in the subspace, and therefore this linear combination must be unique. All right, so since we have this, since you just put in 0 for each of those r's, that must equal 0, right? 0 times W1 plus all the way through 0 to WK, that equals the 0 vector. So since this is true, and there's only one way to get it, right? I mean, so this definitely equals 0. There is only one way to get this to be 0. So that it must imply that R1 through Rn, it has to be 0, okay, because it is unique. All right, so R sub I is equal to 0 for all I equal to 1 to k. Okay, so this basically is by the definition. You must have a unique linear combination to form that. And since you put in 0 and you get that, then that is the vector in question. And so, yes, they're all 0. Now let's go the other direction. So sometimes you'll see this arrow going the other way like that. And we will now suppose that we will suppose that this is unique. All right, and then we'll show it's a basis. So to show it's a basis, we need to express every vector in W as a linear combination of those. Okay, so let's take a look what that would say. So suppose 0 W1 plus 0 W2, etc., 0 WK is equal to the 0 vector is unique. Right, so that has to be or must be the only linear combination that gives you the 0 vector. So now this is using the uniqueness part. So now let W equal C1 W1 plus, etc., down to CK W sub k, and let W equal basically something different, right? Two different possibilities. We'll use D1 W1 to D sub k W sub k, B2 two different representations for W in W. So for the vector W in the set W, which is a subset of Rn. So right now, I'm just assuming that 0 is a unique linear combination of those. So I'm saying, let's suppose this is the linear combination, and oops, not this one, right, is a unique linear combination that gives you the 0 vector. And we basically know it has to be the only one. Now I'm saying let these two different ones be two representations of W. Now, if we can show that W is unique, because it's arbitrary, and we can show that it's unique, then it represents any of these, and it's unique, and therefore it must be a basis. Okay, so think about that. So what you do is basically subtract them. So since we have 0 equal W minus W, right? I mean, it's basically just subtract 2. And so we're going to subtract and factor and rearrange. So it'll look like this. C1 minus D1, W1, etc., all the way to C sub k minus D sub k, W sub k. So 0 must equal that. And the only way to get that is if C1 minus D1 are each 0. So each of those must be 0 because of our initial assumption, and we know that has to be true. So since that 0 equals all of that, we have C1 minus D1 equal to 0. Well, actually, I just kept going across, basically. Each of those are equal to 0. So C1 minus D1, etc., all the way to C sub k minus D sub k, all must equal 0. So C sub I must equal D sub I for all i's, for all I equal to 1 to k. So they're the same thing. So basically we just showed that that linear combination is unique because it must be the same. So you end up getting C1 equals D1, right? So those all have to be the same, in which case, if all of these are the same, then W is unique and therefore a basis. So, by definition, oh wait, I got ahead of myself. Okay, let me first say it's unique, right? So, therefore, W is unique. It's like I have it written down. I just gotta. But I'm trying to discuss it with you somehow. Therefore, it's unique. So, by definition 1.17 to be exact, the set W1 to W sub k is a basis for W. All right, so this also, one reason I do this proof for the class is we're getting into the concept of linearly dependent and linearly independent vectors. And this has a lot to do with it, of how to express it, and when is a vector 0, and along those lines. So I wanted to show you this one. Okay, let's continue. Oops, bring that down. Let's see where we're at. Okay, we got a few more things to do. So next is theorem 1.16. This is really just what I want to discuss. So theorem 1.16 is when do you get a unique solution for ax equals b? And we're not going to go through this proof, but it's building on the following are equivalent concept. So this is theorem 1.16. This is on unique solution for ax equal to b. All right, and so this is square matrix. So m equals n. So usually we'll say n by n. I'm not really sure why I don't say n by n, but usually it's n by n. So let's let A be an n by n matrix. And then, as we have done before, the following are all equivalent. So number one, unique solution. So the first case is the linear system ax equal to b has a unique solution. So what's equivalent to that, basically? So a unique solution for each vector b in Rn. So basically you take any vector and it has a unique solution to it. It's along the same lines of take the real numbers, non-zero of course, and you take any number in the reals and there is an inverse to give you 1. So if you could always like solve a system or an equation. So if you have ax equals b, like literally like whatever 4x equals 5, you always have a solution to that system, that equation. And that's kind of what this is along the same lines of. There's always a multiplicative inverse because you have the inverse matrix. Well, that's one of them basically. So unique solution, and then the matrix A. So there's a few things here. So the matrix A is row equivalent to the identity matrix. So you row reduce all the way down and you get the identity matrix. So the matrix A is row equivalent to the identity matrix I. 3, A is invertible. The matrix A is invertible. 4, the column vectors of A form a basis for Rn. The column vectors of A form a basis for Rn. So when it's not like there's any repeated or multiples of each other. It's like, but think about what's going on here. I mean, you're basically able to row reduce the matrix A and you get I. Well, once you get I, then those column vectors are basically I, J, K, or E1, E2, E3, E4. if you do this row reduction. If you row reduce and you get something to zero out, well, then it's not, you can't generate all of Rn. You're missing, like a plane or something. Okay, so try to think of this geometrically, at least in 3D, why this might work. Okay, so we're not going to go through the details of anything in that proof, but it's an important one. Okay, so highlight that for you. Okay. Let's see what else I got. A couple more things. Let's do one more. Let's do this example. Determine if these vectors form a basis for R3. And you'll never guess what you're going to do. So determine if the vectors V1, so 2, 2, 6, V2, 6, 0, 8, and V3, 1, 4, negative 1, form a basis for R3. So what you're doing then is you're saying, does the span of those vectors generate R3? That's what we basically mean when we say form a basis. So we're not going to use directly the definition. We can use this now. We can basically use these concepts, and especially this one. The column vectors of A, that's A, form a basis for Rn. So this is R3, right? So what could you do? Well, if you put this in a matrix form for column vectors, and then do what? You do row reduction and see if it is the identity matrix, because these are all equivalent. Make sense? Great. No one's very talkative today. So let's do that. So, and I'm not going to show all the steps. And this is, if I ask you to do it, show it, but you can always check it. It's pretty straight up. So you write down I'll write the column vectors down. So actually, let me do this. Let me write them down like this. So you're basically putting in column vectors V1, V2, and V3 and that would be then a 3 by 3 column vectors. So put them in, I like to usually go rows, but do 2, 2, 6, just so I can see better. 6, 0, 8, and then 1, 4, negative 1, like that. And then, now this is not equal. We're going to row reduce. So now, do your row reduction and see what you get. If you get the identity matrix, then you can apply this theorem, right? So does it form a basis? And then you check to see if it's the identity matrix after you do your row reduced echelon form. So do row reduce echelon form. And you could, if I ask you to do it by hand, then do it by hand. But if not, just use a calculator. And in fact, you do. You get 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the 3 by 3 identity matrix. Therefore, you can conclude they do form a basis for R3. Therefore, V1, V2, and V3 form a basis for R3. Let's see. So then are these, this is maybe an obvious question, but are these V1, V2, and V3 your standard basis vectors? Right? Well, of course they're not. They're not standard. These are your standard basis vectors, right? This is E1, E2, E3, or ijk written as a column vector. So when you do the span of this, you generate all of R3, just as if you do the span of ij and k. You get every vector in R3. It's just you basically have one going this way, and then up out of the plane, and it's all skewed and weird, but they're not parallel and they're not duplicates of each other. Okay. Next, let's see what we have. We'll do one more video to finish the rest of this section. So we still got theorem 1.17, corollary to 1.17, and then the structure of the solution set to AX equals B, theorem 1.18.